Alright, here we go. This is Ryan with PDV Motorsports, and thanks for checking out this vlog. This is going to be one of the first real content additions to the vlog where we're going to go through actual data measured on a shock dyno and review the positives and negatives. Not many positives, but we want to get into the details of BC Racing product and understand what is needed to improve performance. And in order to improve performance, we need to understand where they are out of the box. So the reason for this project was to ultimately avoid making a complete damper line from scratch. I wanted to utilize cheap coilovers that are available and have a lot of penetration in the market already, and I did not want to have to worry about test fitting on vehicles. I didn't want to worry about structural analysis to make sure the damper bodies were strong enough or whatever. All that stuff is very basic. There's no value add. And for me to replicate the design structurally at the lower volumes I would have compared to global BC Racing, I would just be increasing costs to the end consumer. So what I want to do is replace a few key components internally in the hydraulics to improve the performance of the existing design, and that should be achievable at a very low price point. So typically these dampers and many other brands like it at the similar price point are very shitty. They don't do any R&D. There's borderline argument you could say there's any engineering at all, and they really focus on marketing, making it a good brand, sponsoring particular people or particular events to get their name out, and then they saturate the market with their low price, and hopefully from there they grow and add features and whatnot, and supposedly improve performance in the future. But I don't think that's really what's happening with BC. Based on the data that we're about to go through, they have 3 4-way adjustable dampers, but if some of their internal components are the same, their performance is still going to be terrible, regardless of how many adjusters they have. So how do we evaluate these dampers? What do I look at when I want to see a high quality, high performance damper? Generally, at a very high level, I want to see what the friction levels are, how the adjusters work, how much rod force there is, what I can do to improve the curves that I can create on the dyno, meaning if I want to design a completely different main piston that provides more digressivity, even regressive curves, high flow linear, and differences in how oil flows through a piston to improve how that curve looks. That's all on the table. And then consistency between builds. So you can build a left and a right, and if they're far off from each other and they're going on the same car, you do not have a good base to build your tune off of and dial in your vehicle. So consistency is really key, and we're going to take a look at that. Now generally on a cheap damper, all of these things don't check many boxes. So they have high friction, their adjusters are terrible, and in the BC case, the adjuster is a single adjuster that adjusts compression and rebound together, which is even worse than just a bad rebound adjuster. You really never ever, I I can't think of an argument that you could ever want compression and rebound adjusted together. You just don't do it. Charge pressures. Ideally, this is a very simple thing, but clearly from the data we're about to see, you can screw it up. And the comment here on chrome rods is just a comment based on the diameter. So with your charge pressure and your rod diameter, you have a certain rod force. That rod force is a significant contributor to ride harshness. If the rod force is too high, especially relative to your spring rate, it can really dominate and make for very poor ride, very poor tire load control. It's just not. There's nothing good about high rod force. So sometimes these cheaper dampers will use a rod diameter out of convenience and not for the sake of performance. So it might be larger than is otherwise needed. And that just increases rod force. So it's just pressure times area in the area of the rod cross section. Cheap pistons, one linear or one digressive main piston design is not the same as another. Unequivocally true. I think there's going to be some more content later on in the future when I'm designing main pistons for this damper. We can get into why that is. I'd like to run some CFD and show some back-to-back, but pistons are not necessarily a simple, trivial thing. And manufacturing processes also dictate certain features that affect performance. And the cheaper ones have all the bad things and none of the good things. So that's just another area to look at. And then shitty dampers tend to have shitty oil. And when it's shitty oil, usually has poor anti-foaming properties, so it will want to cavitate more. It's got terrible viscosity index, so from one temperature to another, the oil properties change that directly affect the force that the damper generates. So if you tune your damper at 90 degrees Fahrenheit, and you go and most of your driving is done at when the damper's at around 120 degrees Fahrenheit, the tune won't be the same. You will lose force as temperature increases, and you want to lose as little force as possible so that it's consistent through the whole temperature range. Whether you're driving around and it's, you just hopped in the car and it's, or the first lap and it's, 50 to 80 degrees out and the damper hasn't really heat soaked yet. Or it's, lap 50 and you're creeping up to 160, 170 degrees Fahrenheit, and you find that your car just doesn't perform the same anymore. You've lost a lot of the control that you've designed into your damper tune. And you can control that with good oil to some extent. So I just want to go over a couple slides here on what shock dyno graphs look like. I know there's plenty of content on this out there, but a real quick review certainly won't hurt. So constant velocity plots, which I'm showing here in black, green, and purple, are plots where force is measured at 1,000 hertz as the damper is cycled through a single velocity point. So it goes through a sine wave where peak velocity is targeted at whatever you want, but typically it's in 1 inch per second increments from 0 to 10 inches per second for a typical damper plot. And that really shows you a lot more detail on what is happening with the damper throughout the entire range of travel. What you do to create a peak velocity plot is you take a CVP and the force that is created at the peak velocity becomes a point on a line for the peak velocity plot. So you can kind of see with a couple of the CVP plots, I put stars at the peak velocity, and those stars correlate to the red lines where the peak velocity point is used to create that kind of defeatured, generalized red line where it tells you a lot about the tune in general, but it doesn't tell you a lot about what's really happening in the damper. So it's a good comparison between 2-3 different tunes or different from one car to another maybe. But if you want to understand if there's a problem, you're usually not going to see it in a PVP plot unless it's such a big problem. It really skews this point-to-point kind of line versus the detailed data that you get with a CVP. So one of the graph types available is a force versus velocity, and this is absolute or force versus absolute velocity. And you can see at the above 0 is compression and below 0 is rebound. Units can be in inches, kilogram force, newtons, inches per second, millimeters per second. It varies quite a bit depending on where you are in the world and which units you like to work with. But from here on out, we'll be working in pounds and inches per second. Damper tunes are pretty much always presented in this format with a PVP. It's the most basic version of a damper plot. It hides any ugly stuff. So companies that are maybe shy and don't want to show their real performance will show PVPs. And that doesn't mean if you get a PVP you can't ask for a CVP and look at their performance. But generally PVPs are provided and it's just simpler and cleaner. Now this is a force displacement plot. Force displacement plots are based off of CVPs. You cannot make a PVP based force displacement plot. So this is the data at 1000 Hertz through the entire stroke, which in this case is a +1 inch, -1 inch from some nominal position. And it goes clockwise from the 9 o'clock position to all the way around back to the 9 o'clock position. And the upper half again is compression, the lower half is rebound. And the 9 o'clock and the 3 o'clock represent the zero velocity where it's changing direction from compressing to extending. And the 0 point, the zero displacement is where peak velocity would be on the sine curve, sine wave. So at zero displacement, you are transitioning from accelerating to decelerating, whether it's compression or rebound, but that is your peak velocity on the sine wave. So now we can get into the details. BC Racing, part number I-41 for the F3X all-wheel drive 3 Series vehicle. This is a CVP force velocity plot of the front left and front right damper that came in my box, in the kit. So same dampers meant for the same car. These should be identical as close as possible, and I'm checking that to see if that's true. So there's a couple things that stand out here. Number one, they're not identical. In fact, they're too far off. 10% delta at the 10 inch per second, and generally throughout the entire curve, it's close to 10% between the left and the right damper curve, is too much. At Penske, I believe they refuse to ship anything above 5%. So that's the kind of quality standard that I'm looking for, and this doesn't do it. Now, in addition to that, there is some terrible hysteresis. Hysteresis is generally, there's a couple things that go into it, but one of the big ones is friction. And friction is really bad here. We're only looking at, especially on the compression side, 125 max pounds through the sine wave. And you see that on the accelerating portion of the sine wave. But as it starts to decelerate, still in compression, but it's coming back now to the 0 point, this gap that's created is hysteresis. And at 125 pound max, we're looking at 60 to 70 pounds of hysteresis, which is a massive amount of hysteresis for a damper that's in close to the softest position, adjuster position it has available to it. Regardless of it says click 15 of 30, I'll get into that. Generally, the softer the adjuster, the less hysteresis there is. There's some hydraulic effect here, not just friction, but this is clearly dominated by friction, and we'll get into that. So we have mismatched dampers left and right, and we have a lot of friction. Generally not very good. Now, what I'm not going to get into is whether or not this tune is appropriate for the vehicle itself. I haven't installed these dampers yet, so I do not know. I cannot evaluate the actual tune for the vehicle, but we'll get into that in a future date. So this is, again, front, left, and right comparison. We're down at 1/2 inch per second on the force displacement plot. Again, still at click 15 of 30. And what we're seeing here is a gross mismatch at this velocity between two dampers that are going on the same car. On top of that, there's a lot of other problems going on here. I'm highlighting some of them. We have one of the really big ones that's highlighted here is the slope. Typically, you want to see, especially at this very, very low velocity, kind of the square shape you're seeing, but symmetric about the horizontal 0 axis. With this upward slope from left to right, what that's showing me is that there isn't enough gas volume in the physical damper design for the rod diameter and the stroke that the damper has. So gas pressure is increasing too much as the rod compresses into the damper body. So we have this increasing force as the damper compresses. Ideally, this should be as flat as possible. And this goes along with the measured gas pressure, which is also too high. We were measuring initially over 200 psi as delivered from BC Racing, and then all subsequent testing was actually done at 150 psi, because we did some high-speed runs up to 30 inches per second and did not see any cavitation at 150 psi. So there's no reason to go above 150 psi. Really, that's an oversight on BC Racing's side. I have no idea why they would charge the pressure that high. Doesn't make any sense. It increases rod force. It increases friction everywhere. It's just bad and unnecessary, it seems. So there's a lot going on here. You really want to see smoother lines. There's something going on hydraulically, or there's just some serious friction issues that are dominating this curve. And then, especially the oval I have on the right is highlighting some pretty drastic differences from left to right damper, where as the damper is fully compressed and starting to extend in the rebound direction, the blue line, whatever damper that is fairly smooth and consistent, whereas the green line damper actually has a peak initially and then drops in force and then ramps back up again. That is definitely concerning, but not just from the standpoint that there's something wrong with the damper, but it is a completely different characteristic than the blue line damper. So these dampers do not perform the same at all. It's very concerning, and if I was a customer with the intent on racing this vehicle, being competitive, I would be furious, and I'd be asking for a rebuild, replacement, or refund. Since I'm going to be tearing these apart, I don't really care. I'm just presenting what I'm finding. But this really isn't acceptable at all to me, and I would imagine this is probably fairly common with the, I assume, hundreds of thousands of coilover kits that are in the market, and maybe even more. So we're switching over to the rear damper now. This is again force displacement curve, but this is my attempt at a friction test. Now I was dyno limited on what I could do. The dyno would not go slow enough, and ultimately what was happening was it was underpowered, and there was enough friction that we could not actually achieve less velocity because there wasn't enough motor torque at such a low speed. So we had to stick to this 0.13 inch per second velocity for this sine wave test. But really, with a hydraulic dyno or an EMA dyno, I would want to see closer to 0.04, 0.004 inches per second. Very, very slow. That correlates to 1 and 0.1 millimeters per second. That's a industry standard friction test, but it just couldn't be achieved. Regardless, through a bunch of velocities at this lower range, the damper curve didn't change much. So we opened up the adjuster to full soft. We went back to mid setting. We moved it all around. We changed pressures. We changed a bunch of things, and ultimately we determined that the dyno was going slow enough that we're probably really measuring friction, and we're not getting any hydraulic effect that's adding a lot of force to the graph. So the force that we're measuring here, which is that green line, which is the delta on your peak compression stroke and your peak rebound stroke, is how you measure friction, and that is about 50 pounds of friction. Typical OEM dampers can achieve roughly 50 newtons, maybe 70 newtons of friction force, which is, I want to say 15 pounds, I forget offhand, but much, much, much lower friction force. And those are, a million units a year kind of mass-produced garbage dampers, and they are much better performers in terms of friction than these BC coilovers. 220 newtons or 50 pounds is wildly unacceptable. Would never be acceptable on any OEM vehicle, let alone a race car. So this is really bad. This is going to be a high priority to figure out where the most friction is. I have no doubt the rod seal is the major contributor, but it could be, we could find a problem with the main piston or the floating piston, and I'll probably end up changing all three of them. But the rod seal is going to be more difficult because it's going to require a new rod seal housing and a seal, and rod seals for dampers that are good are harder to come by in low volume. So we'll see how that works out, but this is a major problem that should be solved. And I think if this is brought down toward my target, every single customer, if nothing else changes, every single customer will feel this. The difference between 50 pounds of friction and 15 pounds of friction. So temperature sensitivity is another metric to look at, but not super critical. It's important, but certainly less so for street cars than for race cars. And the more racy you get, the more important this becomes. But generally, we're just looking at viscosity index, and the higher that number is, the better. And what that means is that the viscosity of the shock oil changes very little as temperature changes. So you want to have constant performance regardless of temperature. That's all this is, and it's a little higher than I'd like to see. At 20% at the relative very low force actually is really what highlights that this is kind of a lot of we're a little too sensitive to temperature. At less than 300 pounds at 10 inches per second, we're seeing a 20% delta, which it seems like a lot. I think I'm going to change oil regardless. I don't even know what oil they use or how to source it. I'm going to use the oil I know works well, but I expect this to improve just with an oil change. So yeah, along with cavitation resistance, the anti-foaming property, how well it bleeds, things like that. They're probably all going to improve with the oil that I'll use versus the oil that DC uses. Now the adjuster is a real turd. This profile is kind of common. Maybe more often I'll see a straight taper, so like a cone shape, than this curved taper. And I actually think they probably would have been better off with a straighter cone-shaped taper. What's happening here is through the first 15 clicks of a 30-click adjuster, they are only adjusting 50 pounds of force at 5 inches per second. So this is a pretty critical area of the damper curve in terms of performance in the vehicle, what you feel, tire grip, things like that. That adjuster really isn't doing much of anything. After click 15, it does a whole lot. So it really starts to restrict flow through the needle or through the jet, and becomes fairly powerful. And over the next 15 clicks, you have a 300-pound force delta. And ultimately what this means is you have an extremely nonlinear adjuster. Without this data, it's really, you don't realize that you only, out of 30 clicks, you really only have 15, maybe 18 clicks before you're really pretty much at full soft. And you might be making changes, going softer, and not finding performance, or it's tricking you, and maybe there's a mental thing going on, and you think you're finding something that's not really there, because really nothing's changing on the damper, even though you're changing the knob, you're changing the setting. So this is really bad, and I find this fairly common, especially in the cheaper dampers, that there's not enough attention put toward the adjuster performance, especially relative to how important, from a marketing standpoint, adjustability is for these companies. So this has to go. I already have a design in CAD. I might get into that a little bit more, but this is something that comes with experience, a lot of R&D testing that requires a lot of machining and expense. So I'm not sure how much I'm really going to share on the profile that I create, but it essentially is based off of this. So I have my own profile I developed when I was at Strange Engineering, and this was the final test that I ran. And what you're really looking at here is a way too many clicks, but it's for R&D, so that's okay. 56 click adjuster, and each run on the graph is a 4-click increment. So what you can see here is from full soft to full stiff, the increments are very, very linear. You can see that it gets a little bit, what's the word? It's a little bit bunched up toward the full stiff, full stiff end of the range, but that is, it's not bad enough that that I would spend money refining the last 4 to 8 clicks of the profile. So even though this has 56 clicks, I have a extremely linear range, and I can now design a damper adjuster around however many clicks I want, likely 10 to 20, and evenly space those increments. So now that I've come up with this design that has very evenly spaced increments, I can change it so that I have only 10 to 20 clicks throughout the entire range, and I know that every one of those clicks is going to have a very consistent force change with each click. So very consistent, very predictable. Once you see this graph, you kind of know every click is going to add, so many pounds, 5 pounds, 10 pounds, whatever it is, at 10 inches per second, and you just know that, and you don't even have to look at a graph. Once you start working with consistent product, it makes tuning easier without having to run the dyno all the time. The other thing that does stand out here, but isn't really the intent of this graph, is that the check valve works very, very well. You can see there is literally zero impact on the compression side as I've gone through the entire adjuster range. So I have a custom check valve that I designed that is performing perfectly. So that design as well will carry forward into all new product. So that is it. I'm really glad I finally pulled all this data together. We actually ran the dyno in 2021, so quite a while ago, but big shout out to Barry at 3DM Motorsport down in North Carolina now. He's the one that helped me with this, and I believe he wants to keep helping me as we go through this whole process of testing new designs that I come up with now. But the next step is to install these crappy dampers onto my car, which I'm hesitant to do now that I've seen the damper curves. They're going to be so bad I don't even want to drive on them. But it's important, I think, to get the feel that everybody else has when they buy the same dampers. So I don't want to take that experience away before I start making changes to the overall damper tune, as well as the turd polishing effort to reduce friction and other things. So thanks again. I hope this was informative, and please like, share, comment. I will endeavor to respond to every single comment there is. So let me know what you think, and hopefully from here we can build this channel into something that is informative just like this on all things from brake kits to wheel design and power adders and everything else. I really want to grow this into an engineering powerhouse that builds great product for these awesome cars that I think we all love. So thanks again. Have a good day.